In the baseline computation state, a processor executes commands procedurally. It moves top-down, reading one instruction at a time along a strictly linear path. This model encounters an immediate mechanical friction. If you need a program to execute a repetitive task 10,000 times, you have to explicitly write that command 10,000 times. Code built this way becomes massively redundant. The linear sequence stretches indefinitely, consuming memory and exposing the architecture to a high probability of manual error. Computer science solves this redundancy through computational iteration. We collapse linear strings of repetitive commands into a single structured block of logic. Instead of processing commands strictly forward, the execution sequence pivots into a closed cycle. We call this architecture looping. By rerouting the execution path back on itself, a loop processes massive datasets and automates workflows using a fraction of the raw code. Linear code scales in exact proportion to the number of tasks required. Iterative structures allow a finite set of elegant commands to execute near infinitely. The immense computational power of this cycle depends entirely on a single operational node, the loop control variable. This variable functions as the absolute state manager for the entire execution cycle, governing the transition between active instructions and the system's eventual termination. Regardless of the specific programming language compiled, this single variable dictates exactly when a loop begins, how long it runs, and when it ceases execution. All iterative algorithms operate as strict state machines. They require continuous, exact parameters to function. Manage this state correctly, and the sequence terminates safely, returning control to the broader program. Mismanage it, and the entire system crashes. The moment control over this variable is lost, the algorithm enters an infinite loop, endlessly consuming processing power until the application freezes or the system shuts down. Initiating a computational process is trivial. The primary task of a programmer is architecting its precise, inevitable termination. This flowchart outlines the three-phase lifecycle required to maintain structural integrity within an iteration cycle. Phase 1 is initialization. Here, the programmer assigns a starting value to the control variable, establishing the valid context and determining where the topological sequence begins. Phase 2 is the test. The test defines the explicit exit condition. Crucially, the machine evaluates this condition before every single iteration begins. If the condition evaluates to false, the sequence aborts. Phase 3 is the update. Inside the loop, the system must actively modify the control variable. This mathematical adjustment drives the system closer to the exit condition with each passing cycle. This snippet shows how these three conceptual phases govern real-world engineering. The initialization sets I to 0. The machine evaluates the test, checking if I remains less than 10. Finally, the update increments I by 1, guaranteeing the cycle will eventually reach 10 and stop. Omit or improperly format any one of these three phases, and state management fails. The result is a broken algorithm. This graphic introduces the first major divergence in iteration architecture, the definite loop. A definite loop executes a fixed, predetermined number of times. Engineers deploy this architecture when processing tasks across known boundaries, like fixed datasets or arrays. Generating the first 10 numbers of the Fibonacci sequence requires exactly 10 cycles. The volume of processing is established before the loop ever runs. Because the topological space is predetermined, a definite loop is highly predictable. Its termination is a mathematical certainty. This slide shows the industry-standard syntactic construct used for definite loops, the for loop. In both the Java and C++ implementations, the syntax physically consolidates the initialize, test, and update phases into a single line of code. Python streamlines this even further, using the range function, which handles demaison variable updating entirely in the background. Despite the surface-level differences in syntax, all three languages strictly execute the exact same three-phase control architecture. Definite loops operate as closed ecosystems. The safety parameters and termination conditions are locked in before execution begins. This graphic details the opposing architecture built for unpredictable environments, the indefinite loop. Here, the total number of iterations is completely unknown beforehand. The system must react dynamically to changing conditions as it runs. As outlined here, this architecture is mandatory when a program continuously waits for user input or monitors live streaming sensor data. To stop the process, developers program a sentinel value, a specific data point, like a typed character, acting as an external kill switch. This infographic shows how the dynamic environment forces a modification of the standard initialize, test, and update sequence to prevent system lockup. This specific safeguard architecture relies on prime, test, and prompt. The critical alteration occurs in phase 1, priming the loop control variable. Priming guarantees a valid initial state before the first evaluation. The system pulls an initial piece of external input, so it never tests null data. Furthermore, phase 3 is no longer a strict mathematical update. It becomes a prompt, actively pulling fresh environmental data from outside the loop into the system. Indefinite loops trade the mathematical safety of predetermined bounds for real-time reactivity. This trade requires absolute precision in state management to avoid catastrophic infinite execution. This matrix provides a final, unified comparison of the two distinct iteration architectures. The definite loop relies on predetermined execution spaces and fixed topologies. The indefinite loop relies on dynamically monitored states and active external prompting. Despite targeting completely different engineering problems, both systems live or die based entirely on the strict management of their loop control variable. High-level engineering places termination logic on equal footing with execution, creating systems that know exactly when and how to stop.